Math 1325, we're going to be on Tuesday, July 26th here, and we're scheduled to work on sections 3.3 and 3.4. 3.3 has two main concepts. The first one is something called, go back to this question, average rate of change of a function. So let's say our function is 9x to the third plus 9. This is problem number 1. F of x is 9x to the third plus 9. This is a graph that sort of looks like this. And we want the average rate of change between the 2 and 4, the interval 2 to 4. So 2 to 4, something like that. When x is 2, when x is 4, what's the average rate of change of the function? So average rate of change, is a fancy way to say slope. Think of average rate of change equal to the slope in algebra. So when you're on a curve like this, and maybe if I blow this section of the curve up, say you have a curve like so, and you are here and there as a starting and stopping point. If you could figure out the slope at every spot along the path, some of these slopes would be flat, then they get a little steeper, steeper and steeper and steeper. If you could somehow get every single slope and average them all out, that's the average rate of change between these 2 points. But there's an infinite number of spots in between, so there's no way to actually do that. But if you just take a straight line between these 2 points, the slope of that line turns out to be the average of all these individual ones. So average rate of change is no different than slope. In algebra, they say y2 minus y1 over x2 minus x1. In calculus, they usually put f of b minus f of a over b minus a. And when you're given an interval like this from 2 to 4, the smaller one is a and the bigger one is b. So the denominator is literally just 4 minus 2. And the numerator, f of 4 minus f of 2. F of 4 is the y value when the function has an x value of 4. So you just figure out f of 4 first. 9 times 4 cubed plus 9. 4 cubed is 64 times 9 plus 9. So f of 4 is 585. And then if I do f of 2, 9 times 2 cubed plus 9, sorry. 2 cubed is 8. 8 times 9 is 72. 72 plus 9 is 81. So it's like in algebra having the coordinate 2, 81, and this spot up here, 4, 585, and trying to find the slope between those two coordinates. So the average rate of change for this first example is 585 minus 81 over 4 minus 2. And the denominators are usually easy, as whatever you subtract the given interval to be. 585 minus 81 is 504. Divided by 2 is 252. So again, some of those slopes are more steep than others, but it would average out to 252. The average rate of change over the interval 2 to 4 is 252. Then if I repeat it for the interval -3 to 3, part B, -3 to 3. So I need to do f of 3, you always do f of B first, minus f of A over B minus A. And it's the same function for both parts, 9x cubed plus 9. So plug in 3 first. 3 cubed is 27. 27 times 9, and then plus 9. So f of 3 is 252. F of -3 cubed is -27 times 9 plus 9 is -234. And the same way the denominator is a double negative. When you're subtracting like this and you get a double negative, that's the same thing as plus. So the bottom is 3 plus 3, 6. So the top is 252 plus 234. 486 divided by 6. And since 48 divided by 6 is 8 and 6 divided by 6 is 1, this should be 81. So the average rate of change there is 81, not quite as steep as the other ones. And that's because the 2 to 4 interval is already on the side of this curve where it's starting to shoot up pretty fast. But if you go from -3 all the way to 3, you've got this flat portion that's going to bring the average down a little bit. So it kind of makes sense that it has a smaller answer than part A, 81. That's one of 2 topics in this section 3.3 is doing average rate of change. And if you think of algebra slope, it's a very similar concept. Oops. Okay, same problem, just a different function. The square root of 5x plus 1 is our function, and we want to just go between 3 and 7. Average rate of change for number 2. Y equals, or f of x, those are synonymous, the square root of 5x plus 1. And we want the average rate of change between x equals 3 and x equals 7. The bigger one is always b, and the smaller one's always a. So f of b minus f of a over b minus a. So I need to do f of 7 minus f of 3 over 7 minus 3. The bottom's always easy. 7 minus 3 is 4. Plug a 7 in here. 7 times 5 is 35 plus 1 is 36. The square root of 36 is 6. 5 times 3 is 15, plus 1 is 16. The square root of 16 is 4. So 6 minus 4 is 2, and 2 divided by 4 is a half. Now square root functions are, the parent function of it anyway is like this. So this is a lot less steep than the one we were just doing. So if you go between 3 and 7, it's somewhat slope, but it's getting less and less and less, although it never gets horizontal. So this kind of makes sense. It's much smaller than the last 2 answers of just 1/2. Type an integer or a simplified fraction, so they won't take 0.5, and they would count 2/4 wrong, so this is 1/2. Okay, so same deal, just got a exponential function, y equals e to the x between -2 and +1. Still ask for average rate of change. From -2 to +1. So A and B, f of 1 minus f of -2 over 1 minus -2. F of 1 is e to the first power. F of -2 would be e to the -2. And then the denominator, this double negative will switch to plus, and it'll be a 3. E to the -2 could be changed to 1 over e squared, potentially, if that's more helpful. And e to the first is just e. So I'm checking what they want. It says round to 4 decimal places, so that means we're just going to be using a calculator to approximate this to 4 decimal places. So most scientific and graphing calculators have E. On here, it's apparently right there. Let's clear this. And that's just exponential. Wait a minute. Okay. Oh, here it is right there, E. E is 2.718281828, and then it's sort of like pi, how it's just a long, messy decimal that keeps going on and on and on. So think of E as 2.71828. It's about 2.7. They want 4 decimals though. 1, 2, 3, 4. So you'd have to make this a 3. 2.7183. That's what E is. And I can square it. Oops, I square rooted it. Sorry. Square it. Okay, there it is, squared. And then if I do 1 over it, that's what the second half of this fraction would be. So I need, if I round this to 4, 1353. So then we need to subtract that, minus 1353. And the denominator is just 3. So let me try this. One issue is you don't want to necessarily round these to 4 decimal places in the middle of the problem. So I'm going to leave this whole thing here. And even though I need it the other direction, I'm going to minus E, which will be the opposite sign. So let me switch it. Yeah, it should be positive 2.5. And then divide by 3. Now you round to 4 places. So this 8 right here, you need to add 1 to the 9, make this 09 turn into a 10. So 0.8610. So this just gets messy because we need to work in decimals with these long, messy exponential and the fact that they don't come out exactly, so you have to work in decimals. So 0.8610, round to 4 decimals. Okay, so the first 3 problems were average rate of change. Now we switch to instantaneous rate of change, or in this case, velocity, but that one's velocity too. Here, let me do this first. Find the instantaneous rate of change. That's the second big concept here. It just turns out that velocity in physics is a concept of this. But let's just do the ordinary function first. So 4, 5, this should be number 6. We have a generic function x squared plus 5x. And then they give me one specific spot. I want to know the instantaneous rate of change there. So what's the slope exactly at that one point? So if you were to graph this parabola, something like this, and you went to x equals 2, instantaneous rate of change is like the slope that just touches it one time. Average rate of change is a slope that goes through the curve twice. Instantaneous rate of change touches the curve once only. It's called tangent. So if I could put a tangent line on this curve exactly when x equals 2, what would the slope of that line be? And again, if you notice, it would change from point to point. There it's negative, a steep negative. Here it's less steep. Right at the origin, it would be horizontal. Then it starts going positive and larger and larger and larger. So that's why velocity is an application of this. Velocity is how fast are you moving at any one point. Where average rate of change for a car is just what's your average speed over a certain period of time. So what happens here is we do f of x plus h. H, you just go a little bit past the one you want to do. And then you minus the original f of x. And divide by h. You may have seen this before in a college algebra class. They teach this, and they call this the difference quotient there. And then you do all the algebra behind it. And then later when you get to calculus, they add one little calculus concept in the front. What we were doing yesterday, limit as h approaches 0. And that's the idea, is that I can't plug 0 in right now, so we're going to have to do something about that denominator. And then you can do this, later we'll do this in terms of x, but we can also be given an x value and just work with the number, which makes things a little easier. So limit as h approaches 0 for f of 2 plus h minus f of 2 all over h. So stick a 2 plus h in these two x slots. That's what f of 2 plus h is. So I like to put a bracket around this to know when it starts and stops. So I'm going to have a 2 plus h squared for this part, plus 5, and then another 2 plus h right there. This whole expression is f of x plus, or f of 2 plus h. Minus f of 2, now just stick 2's in for each of those slots. 2 squared plus 5 times 2. So I like to put a bracket around this. There's the minus, and then a bracket around this. So that way we can keep them separate, which one's which. All over h. And the whole issue here is I can't plug 0 in because it makes the denominator 0. So when we simplify the top, we're going to be able to eliminate the h in the denominator. Now you're going to do this binomial squared right here a lot. So it helps if you can do a shortcut. If you can't, then you should write it twice and FOIL it out. But it turns out the shortcut is you square the front term. That would be a 4. You multiply these two together and double it. 2h doubled is 4h. And then you square the last term and get h squared. And then I can do distributive property 10 and 5h. So all of that right there was f of x, f of 2 plus h. And then 2 squared is 4, so I got a minus 4. And 5 times 2 is 10, so minus 10. And even though I could have combined the 4 and the 10 here, I could combine the 4h and the 5h. It actually helps if you don't, because if you notice how many terms are in the original function, there's 2 terms. So there were 2 terms here in f of 2. And I got minus 4 and minus 10 for those 2. So whether there's 1 term here, 2 terms, 3, or a whole bunch, if you do this properly, this is kind of a double check. The negative 4, there better be a positive 4 in here in the f of 2 plus h part, and there is. That always cancels. This negative 10 better have a counterpart that it cancels with. That always happens. So instead of combining like terms and then subtracting, you can do that if you want, but it's quicker this way, and it's always a nice double check, because if that's not true, you did something wrong up to that point. So all we have left is 4h plus h squared plus 5h. So then you could combine that and make this 9h if you want. And then I'm still stuck with this limit because I can't plug 0 in still to this point. But the numerator has a greatest common factor of h. So if I pull h out, and we had some problems like this yesterday, then you're left with 9 plus h. But that GCF h will cancel with the bottom. And now there's no issue plugging 0 in because it won't make the bottom 0. So the limit as h approaches 0 of 9 plus h, that's a polynomial. Then you can just plug the 0 in. 9 plus 0 is 9. So the slope of the line right here, this isn't the exact graph of this, but just approximately, that slope would have a slope of 9. It would be going up 9 over 1. And then if this is like a vehicle traveling, this is the graph of the vehicle's speed changing, the vehicle would be going 9 miles an hour at that point. That would be its instantaneous velocity, as an example. That wouldn't be the perfect example, only going that fast, but so the instantaneous rate of change is the slope at any one given spot. 9, and that's something they don't do in algebra. Algebra just does average rate of change. It doesn't do instantaneous. It takes calculus for that because you have to know how to do a limit. Okay, so back to this one with a velocity. So instantaneous velocity is like instantaneous rate of change. And they're giving me a t value. That's like the x value in the previous problem. So t squared plus 4t plus 5, t equals 2, or these two problems are identical, really, just different numbers. So I'm going to do number 5, and I'm sure you could go back and do 4 yourself. And I want to do this one because it's a little different. It's got a different t value. So here is number 5, and then 4 will be slightly easier. So in physics, they call this the position function s of t. Where is the object or the car at any given time? And it's a quadratic function, 4t squared minus 3t minus 10. And then I'm given an arbitrary time of 3. So the instantaneous velocity is similar to instantaneous rate of change. We do limit as h approaches 0. And then rather than f of x plus h, we have to switch to s of t plus h. Since it's not f of x, it's s of t. And then minus the s of t all over h. So a good way to remember that is it alternates th, th. Or in this problem, it was xh, xh. So f of x, s of t, s of t. That's always going to be the first and the third thing. And then what the adding h deal does, if you have these curves, if you have a curve like this, you remember when we did average rate of change and the 2 points were far away from each other? So then the line goes through the curve twice. That's average rate of change. That's called the slope of a secant line. If you do f of x plus h or s of t plus h, the plus h means, what if I just add a very, very tiny amount where the limit as t approaches infinity? So, approaches 0. I said that wrong. Limit as h approaches 0 is the idea. In other words, h is going to get really, really close to 0. Not 0 exactly, but really close to 0, 0.000001. So what that does is it moves this point right next to the other one, so close the human eye might not even be able to tell them apart. They're so close together that the average rate of change only touches it once instead of twice. So you've moved from average rate of change to instantaneous rate of change. And you've gone from a slope of a secant line to a slope of a tangent line. So that's the reason for the limit as h approaches 0. And that's why you add h. You just add a little bit to your spot, a little bit past 3 in essence. So if they give me a t value, which they're not always going to, but here they are, so then you can put 3 in for t. But later we'll do this with just variables there too. The advantage of doing it with a variable is if you want to do another time, right now, if I do this t equals 3 and then I say, okay, wait, I want to do another one when t is 5, then you got to rework all this algebra all over again. But if you do it in terms of t, then you do it once and then you can plug in any t that you want, which makes it more convenient if you're going to be doing more than one value. Okay, so I need to do 3, let me write it out first. S of 3 plus h minus S of 3 all over h. So you need to stick this 3 plus h in for the 2 different t's here. And this is why I like to put a bracket for this to keep track where does it start and stop. So I've got a 4t squared. I need to have 4, replace the t with 3 plus h squared. Then minus 3t, so minus 3 plus h. And then minus 10. The other one didn't have this minus 10, but now we have that, so that's fine. That bracket is S of 3 plus h. Minus, and now I'm going to do another bracket for S of 3. Put a 3 there and there. 4 times 3 squared minus 3 times 3 minus 10. So this time there's 3 terms in this slot. So we want to square this first. And this is what I said, you're going to do this a lot. It's 3 squared, which is 9. You multiply this together and double it. 3h doubled would be 6h. And then you square the h. And then I got to distribute this outside 4. So 4 times 9 is 36. I'm going to try to leave enough room this time. 4 times 6h is 24h. 4 times h squared is literally 4h squared. Then I've got negative 3 times 3 is negative 9. This can get long and messy. Negative 3 times h is negative 3h. And then the minus 10. So it turned out there were 6 terms there, and none of them, well, there's a couple of like terms actually. But don't put them together because we got 3 terms over here. When I'm done with these 3 terms, they're going to have counterparts in here they cancel with. And then the whole thing will be over h. So 3 squared is 9. 9 times 4 is 36. And then you're going to put a negative on it to make it negative 36. And then there should be a positive 36 it cancels with. Yep. Here's negative 3 times 3. So at this point, it's negative 9. But then the negative on the outside turns it to positive 9. Everything in here switches to the opposite. Positive 9. There better be a negative 9 to cancel it. Yep. And then there's just a negative 10 here that would turn into positive 10. And that cancels with the negative 10. So all of your terms in the second bracket always cancel out. If they don't, you did something wrong. And notice I only have 3 terms left. Sometimes there's no like terms among them. Here we're getting some that are. The 24h and the 3h could be combined together. So we're left with, in whatever order you want to write this, 4h squared plus 21h. over the denominator h, and we're trying to do the limit as h approaches 0. But I can't plug 0 in until I factor out the h off the top. Whoops. H times 4h, you took one of the h's away, and then plus 21, and you took the h away. So boom, boom, those cancel. Now I can finally plug 0 in. 4 times 0 is 0. That always just disappears. So the answer is right there, 21. The instantaneous velocity of this object is 21, whatever units it's about. And that's similar to the instantaneous rate of change in the generic function problems. And so you get all this algebra here. This is very typical in calculus where there's all this algebra going on. And the only calculus is the very last step. Just plugging a 0 in, that's the calculus side of this. And a junior high kid could probably plug a 0 in and tell me that 4 times 0 is 0. But a junior high kid would be completely lost in all this algebra. So that's what's strange, is that calculus, the hardest parts of calculus often are all the algebra and maybe the trig stuff you have to do. This class doesn't have a lot of trig to it, but it's hard to get to the calculus part of it sometimes. So 21 is the instantaneous velocity of that object at time equals 3. So question 4 is exactly like question 5. You just get to practice a little more. But everything here is positive, makes it a little bit easier. And we already did one with a 2, so I just wanted to do a different one. But other than that, 4 and 5 are identical. 7, now this is a case again, if you go to view an example, some of these problems get quite long. And part of the issue is we haven't learned how this works yet. That's going to come down the line later. So go to this, like, view an example or help me solve this. And what ends up happening here is you're kind of doing what we were just doing on those other problems. But then you kind of get stuck at a point where even they mention here it's extremely difficult to simplify this because you haven't learned how to do that yet. So you've got like logs inside of exponents. So then all they do here, and this takes a long time actually, is they start plugging in. First they plug in 1 for the h. They let h equal 10 to the 0 power 1. Then they do 10 to the negative 1, which is just 0.1. Then 10 to the negative 2 is 0.01, and they're just plugging it in this and letting a calculator tell them the answer. Then 0.001. This is kind of how we were doing limits by the table method last time. 0.0001, 0.0001, and they just keep going for a long time here until they get an answer that repeats. This is also the idea of a limit. The first answer was 8.6 when you plugged 1 in. Then when you plugged in 0.1, it dropped to 5.8. Then 5.6, 5.6, 5.6. It's starting to level off around 5.6. And then it was 5.6035, 5.6034, 5.6034. So now it's stopped at that value when you're just rounding. It keeps going, but if you round to 4 decimals, it seems to stop. So that's the instantaneous rate of change then. And then they even mentioned you could just use a graphing calculator and do what we did last time. So again, I don't want to make these videos too long and you get bogged down in a problem like this when it's going to be taught again later in a better way. But right now you can't do a lot with it other than just use a calculator and plug in decimal after decimal after decimal to figure out the answer. And then this is just what's the difference between average rate of change and instantaneous rate of change. So you can eliminate 2 of these 4 choices because average rate of change is slope. y2 minus y1 over x2 minus x1. Though that formula has minuses in it, not pluses. So it's not A or D. That's the wrong formula even from algebra. So average rate of change. Now it does say at x equals a, so I'm guessing it's C because that's the one that's talking about exactly at 1 point. Oh no, that's instantaneous rate of change. Okay, so average rate of change, the instantaneous rate of change Yeah, see, it's definitely B, because instantaneous rate of change, you don't use the slope formula on its own. You need to do the limit of it. So the average rate of change is where you're basically using the algebra slope formula in a slightly different looking format. And then the instantaneous rate of change is when you do that, but the limit as B approaches A. So that's B. Okay, and then we have 9, 10, 11, 12. These are all these application problems for business calculus. So let me just maybe do a couple of these and then just leave the rest to you. And again, if you get, the tests aren't going to have these extremely hard, long problems, but the point is that this is a business calculus class, so they want to show you some applications that apply to businesses. So suppose customers in a hardware store are willing to buy N of P boxes of nails at P dollars per box. And we have a function here, N of P is 100 minus 3P squared, and P has to be between 2 and 5. P is the dollars. So they must sell them anywhere between $2 and $5. There's nothing cheaper than 2, and there's nothing more expensive than 5. Find the average rate of change for the price from $3 to $4. So that's the first half of the section's concept. Average rate of change, we're going to do f of 4 minus f of 3 over 4 minus 3. And instead of f of, it's n of p. So this is just taking what we did on the first 3 problems and applying it to a business setting. N of p, the cost of number of nails that this hardware store sells, is 100 minus 3p squared. And in part 1 or part A, we want to do average rate of change, not instantaneous, but average rate of change. Oops, I should put P, not X. From P equals 3 to P equals 4. So we need to do N of 4 minus N of 3 over 4 minus 3. So 4 squared is 16 times 3 is 48. 100 minus 48 is 52. 3 squared is 9 times 3 is 27. 100 minus 27 is 73. 4 minus 3 is 1. That's negative 21 over 1, or negative 21. And the reason it's negative is, this is very common in business, if you buy in a larger quantity, you get a better price per item. So that's why people buy in bulk. So then what you're paying per nail is lower. So if you go from the $3 box to the $4 box, you're saving by doing that. The average rate of change of the demand, and that's another thing too, I missed the part about demand. When price goes up, demand goes down. So higher price things aren't as in demand as lower priced ones. So that was average rate of change. Now find the instantaneous rate of change at $3 exactly. And that's exactly the whole point of this section 3.3 is average rate of change is like slope. And then when you switch to instantaneous rate of change, you apply this calculus concept of a limit. The limit is h approaches 0, and I want to do n of, what was it, $3? $3, so we do 3 plus h minus n of 3 all over h. So that way we're doing 3h, 3h. So limit is h approaches 0. Stick 3 plus h right where that p is. So 100 minus 3 times that squared. Here's my bracket, 100 minus 3, and then 3 plus h is replacing the p squared. That's the 3 plus h portion. Now I'm going to do it for just plugging 3 in. So 100 minus 3 times 3 squared. this function that we're working with only has one variable. The last couple we did had two different variables in the function. It just depends what you got. And then all over h. So again, this is a nice binomial squared that if you can square it out quickly, it's 3 squared 9. 3h doubled is 6h. And then h squared. So I've got limit as h approaches 0. There's the 100. And then I'm going to distribute this -3 and get -27, -18h, -3h squared. That only has 4 terms, and the last time we did one we had 6. So now put the negative on this stuff. There's -100, and that should cancel. Yes, it does. So figure this out first. 3 squared is 9. 9 times 3 is 27. So at first it's -27 in here, but then the outside negative switches it to +27. But then there should be a -27 to cancel it. Yep. So notice there's only 2 terms left, and they both have h, and there is no like terms this time. So we can right away factor out the GCF. H is the GCF. There actually 3h would be the GCF, but you can just take h out because that's the part we want to cancel. So it doesn't matter if you take 3h or just h is easier. So there'd be a -18 for that part. And then you took 1h away, but there's still 1 there, so -3h. Then boom, boom, those cancel. Plug the 0 in, and you're left with just the constant -18. So when the price is set at $3, the demand is dropping by 18 at that point, at that instantaneous moment in time. And then just do it again for $4. I'm going to skip that part for now. So I'll just put in a wrong answer and see what it says. The answer is, you do that exactly the same way as part B, just you're using 4 instead of 3. So it turns out that's a -24. So it's a steeper negative because as the price goes up, the demand goes down. So it makes sense that at that moment in time, even less customers would want to buy that. And okay, that was the last part of it. So really, part A, part B, if you can do both of those, you understand this question. They just gave us 2 versions of part B in essence. And then maybe we'll do one last one here at the end, number 13. The distance of a particle from some fixed point is given by this. This is a position function. What is the average rate of change from 3 to 4? So there's at least a part A. There must be a part B that's probably instantaneous change, so that way you're getting to practice both concepts in this section. So we have a position function like in physics, s of t. It's a quadratic t squared plus 5t minus 2. Part A, we're doing average rate of change from 3 to 4, which you could say that, or you could put bracket 3 comma 4. That means between 3 and 4 too. So we need s of 4 minus s of 3 over 4 minus 3. This is like slope. There is no limit here. Average rate of change is like algebra. Instantaneous rate of change is calculus. S of 4, so 4 squared, 16. 5 times 4 is 20. That's 36 minus 2 is 34. 3 squared is 9. 5 times 3 is 15. 9 plus 15 is 24. Minus 2 is 22. So the top is 12. The bottom is 1. This particle is moving at 12. Whoops, sorry. So the instantaneous, this is average rate of change. So that's on average 12 units over that whole interval, even though it may be changing constantly at every specific spot. But if you had a curve, then it would be like the average of all those slopes. what is the, okay, so all they did was change this. That's the same thing. I'll just get it wrong. So you do that exactly like part A. They just change, it would be S of 5 minus S of 3 over 5 minus 3. So it just increased from 12 to 13 by increasing the interval. And then what's the instantaneous rate of change at 3? That's the other half of the problem, or other half of the section. So I'm going to skip right to part C. Instantaneous rate of change at 3. So limit as h approaches 0. S of 3 plus h minus S of 3 all over h. So stick 3 plus h into both of these t's. Now there are 2 of them to plug into. So we're going to need 3 plus h squared, which we've already done twice today, plus 5 times 3 plus h, plus, or minus 2, I'm sorry, minus 2. That whole bracket right there is 3 plus h. Minus S of 3, so 3 squared plus 5 times 3 minus 2. The second bracket's got 3 terms, so these 3 will cancel 3 of whatever. This will probably turn out to be 6 again. So we've done this twice already. 3 plus h squared is 9 plus 6h plus h squared, and this time there's nothing in front to distribute onto it. So I'm just going to write those 3 terms. 9 plus 6h plus h squared. Then here I can distribute 15 plus 5h minus 2. It took 6 terms to get that all the way out. 3 squared here is 9, but then you put the negative on it and you get negative 9, and then it should cancel with positive 9 somewhere in the front. Yep. 5 times 3 is positive 15 in the bracket, but then you're going to put the negative on it and make it negative 15. And then it should cancel with positive 15. Yep. And this negative 2 in here, when you put the negative on it, it'll switch to positive 2. And there should be a negative 2 to cancel it. All the remaining terms have h in them. And there's even a set of like terms. 6h plus 5h is 11h. So I can either write 11h plus h squared, or the other way around, h squared plus 11h. But the top you can factor out h, even if there's more that you could factor out. So you don't need the full GCF, just h really. That'll cancel this. Now you can plug 0 in. So the instantaneous rate of change of that particle is 11 right at that moment, or its velocity is another way of thinking about it. So 11 is the instantaneous rate of change, or velocity. And then, yeah, okay, that's it. So see what you can do with the rest of this. And if you have any issues on any of these other ones, just email me. But we're already 50 minutes in, and we've got to cover another section today too. So the other section, 3.4, let's see what's going on here. And then tomorrow we'll do 4.1 and 4.2. Thursday you can review, and the test will appear right here. And if you review on Thursday and maybe even a little Friday, then take the test on Friday is usually a good plan. But if you think you're ready, you can do it on Thursday. Okay. Okay, so by considering but not calculating the slope of the tangent line. Okay, I think I see what they're saying here. Whoops. Okay, so we have a constant function given first, f of x equals 6. F of x equals 6, that's y equals 6. Algebra knowledge, that's a horizontal line right through 6. This concept is one of the major topics of calculus. It's called a derivative. But a derivative is literally what we were just doing in the last section. It's the slope of a tangent line. Slope of a tangent line. It's the instantaneous rate of change. So you go to any one spot on your function, draw a tangent line, and ask yourself, what's the slope of the tangent line? Well, a tangent line to a line is parallel to it. So if it's curved, that's not going to be the case, but for a straight line, all points on the line, the tangent line is parallel to it. So whatever the slope of the original line is, that's the slope of every single tangent line you could possibly draw. And all of those tangent lines are horizontal then. Since the original line's horizontal lines have a slope of 0. So that's the point of this problem, is the derivative of this function is 0 just because the slope would be 0 of any of those tangent lines. And that's why they said do it without calculating, by considering but not calculating the slope of the tangent line. So I can tell those tangent lines have slopes of 0. So therefore the derivative is 0, because that's what a derivative literally is the slope of a tangent line. What about if you have y equals x? Y equals x, f of x equals x, or y equals x, that's a diagonal line at a 45-degree angle. Well, every tangent line you could possibly draw is parallel to that. So lines are not that interesting for derivatives because every spot has exactly the same slope. And the tangent lines, no matter where you draw them, they have the same slope as the original line. So derivatives don't get exciting until you get to at least a quadratic and have some curve in the graph. But clearly this is a slope of 1 right there. So all these tangent lines have to have a slope of 1. And that's what the derivative would be here, is 1. Whoops, I keep going here because I'm used to that from another class. But okay, the derivative is 1, since the slope of the regular line was 1. Negative x, as long as it's linear, it's whatever the slope is. So negative 1. The line x equals 2 is a vertical line and has an undefined slope. So if the slope's undefined, the derivative does not exist. You can't do slopes. You can't do the derivative when it's a slope of a tangent line if the tangent line is vertical. And then if you just have a generic diagonal line mx plus b, the derivative is going to be m, because that's the slope of that line and it's just a line. Okay, so that was all line. Okay, so where is f not differentiable? Differentiable is the verb for doing a derivative. So if I say find the derivative, then the process of doing that is called differentiation, or is it differentiable? So you're not going to be differentiable at any spot where the original function doesn't exist, if the original function is undefined. So the original function is undefined at 4. So x equals 4. There's actually a vertical asymptote there. So if the graph doesn't exist somewhere, you can't do a derivative. You have to be able to draw a tangent line at a spot. So if there's nothing at that spot, there's no derivative, literally. Okay, so this is the idea when you have a curve. If you have a curve, you pick a spot, or maybe they tell you where to go. Here's a spot, so they drew a tangent line right at that spot. This pink or red dotted line, if you knew the slope of that line, that's the answer to the derivative. But it's on a curve, it's different at every spot you go to. If I go right there, the tangent line would be horizontal. If I come over here, the tangent line would have a positive slope. This is definitely a negative slope. Estimate it, rise over run. Okay, so what if I go, is there any exact spot? It doesn't seem like it goes through anything exactly. So this is really a rough estimate. Maybe they're going to be lenient on us. But if I go down 1, it's not even over 1. How about down 2, over 1, roughly. So maybe -2, round to the nearest integer. Okay. That's the idea. You just want to draw it right on there. So here's an easy one, because if the red tangent line is horizontal, that has a slope of 0. So the slope of the tangent line is 0, so therefore the derivative of that one spot is 0. Okay. Now I know what they're doing next, but let me see if this is probably a better example to do first. So I'm going to do 6 first, and I'll go back to 5. And remember, I actually mentioned this in the last section. So this is going to be very similar to what we just did in the last section, except we're not going to do it at a given value. We're not going to plug 2 or 3 in. We're going to do this in variables only first. So I'm given a function 4x cubed plus 6. So if you do limit as h approaches 0 of not f of 2 plus h, but f of x plus h, we're just going to leave it as x instead of plugging a number like 2 or 3 in. So then it's going to go xh, xh. So minus f of x all over h. So we're going to do this in general terms first, and then it'll be easier to plug in multiple x values instead of doing one specific x value and having to start all over again. So here it's a very similar process. You just don't have numbers to work with as much, but it still comes out, it's about the same amount of work this way too. So I'm going to put a bracket. I'm going to stick this x plus h right where that x is. 4x plus h cubed plus 6 minus, and now this is what's nice, is this is f of x. It's literally right there. You don't even have to do anything. You just literally write down what they say it is. That part's even easier than when you're plugging a number in. Okay, we've seen this as a square before. Now it's cubed. Here's something that helps. If you've ever heard of Pascal's triangle, 1, 1, 1, 1, 2, 1, 1, and then what you do is you add these two and put them halfway in between 3. 2 plus 1's 3, and then there's always 1s on the outside. So this is 0 power, this is first power, this is squares, and this is cubes. So x plus h cubed is going to have 4 terms. These are the coefficients, 1, 3, 3, 1. 1, 3, 3, 1. And then you take the x, and it gets the third power. The h gets a 0 power. And then if this is plus, they're all pluses. And then you do x, and you decrease it by 1 to 2, and you increase the h to 1. Now you decrease the x to 1, you increase the h to 2. Finally, you decrease the x to 0 and increase the h to 3. So all of this, and I'm going to clean it up, that's f of x plus h right there. Anything to the 0 power is 1, and if you have a 1x, is the same thing as x. So you just get x to the third for the first term. This is exactly like it looks, 3x squared h. And this is like it looks, 3xh squared. Those are not like terms. And here the 1 and the x to the 0 don't matter, so you just get h to the third. Finally, I'll distribute a 4 into here, and none of these are like terms, so you just get all this stuff separately. So there's a 4x to the third. Four x to the third. There'll be a 12x squared h. A 12xh squared. And a 4 times h to the third is 4h to the third plus 6. That's the hard part. Here comes the easy part. Just like when we plugged a number in, you're going to switch these to the opposite, and then they should cancel, whether there's 1 term, 2 terms, 3 terms. So I'm going to switch this 4x to the third to negative 4x to the third, and then it should cancel out. Yep. And then I'm going to switch this plus 6 to a minus 6, and it should cancel out. Yep. So what's left? There's 1, 2, 3 terms left. And all 3 of them have an h. So I can factor out an h. Take this h away, you'll have 12x squared left. Take 1h away, you'll have 12xh. Take an h away, you'll have 4h squared. Boom, boom. And here comes the really easy part. I'm going to put 0 in for h. It makes this whole term disappear. And it makes that disappear. Literally, the answer is right there. And because we didn't plug a number in for x, there's going to be an x in the answer. So the answer is 12x squared, although sometimes there's more than one term in the answer. 12x squared. And the way we denote this is the original function was f of x. This is the derivative symbol is called f prime of x. You put a little apostrophe. So that lets the reader know, okay, this is the derivative of the original f of x function. And then the advantage is now I can do any x I want. I can do f prime of 2, I can do f prime of 3, I can do f prime of 4, and it's just plugging in new numbers right here. If you did this process with a number in for x, like 2, 3, or 4, like we did last section, that's fine for that problem. But then if you want to do 3, you got to come back and redo everything with a 3, and then redo everything with a 4. So the advantage of doing it with x is once you get the derivative function, then you can just plug 2, 3, 4, and whatever you want to plug in here. And it makes getting multiple answers easier. So before we just cared about one answer, but we might care about more than one. They want me to do f prime of negative 4, f prime of 0, f prime of 1. I don't want to have to do that limit thing 3 times just because there's 3 numbers to do. So if you want to plug the numbers in, you can do that, but it would take you 3 times the work to do that. So now I can just stick negative 4 where this x is. Negative 4 squared is 16. 16 times 12, whoops, is 192. So the slope of the tangent line exactly at negative 4 on this graph would be 192. And then f prime of 0 would be 0 squared is 0 times 12 is 0. The slope of the tangent line would be horizontal at that spot. And then f prime of 1, put a 1 right here. 1 squared is 1 times 12 is 12. So doing multiple slopes of tangent lines becomes really easy instead of really long and messy. And in fact, if I go back to that, 4x to the third plus 6, well, let me do it right here. The graph of that, it's shifted up 6, and then it's a little vertically stretched, but it looks like this in algebra. So when x is 0, yeah, see how it's flat right here? The graph is just flat at this point. So the tangent line would be flat right there. That's why f prime of 0 is 0. F prime of 1 had an answer of 12. So what that's saying is if x was 1 and you put a tangent line slope right there, it would have a slope of 12. F prime of negative 4 was 192 or something like that. Yeah, 192. Well, negative 4 is way over here. Negative 1, 2, 3, 4. This thing gets vertical, or not vertical, but really close to vertical really quickly. So by the time you get way out to negative 4 on that, your slope is almost vertical. It's a positive 192 way down there. It goes up 192 every time it goes over 1. It's almost vertical, which makes sense if you know the way that graph looks. So what happens if you get 18 over x? How do you find the derivative of that? Back to number 5. It's a similar process. The algebra is just not as long. So f of x plus h minus f of x all over h. This is literally the definition of a derivative. In the last section, they called this instantaneous rate of change. This is the derivative, in essence, formula. Derivative. It's the same thing as instantaneous rate of change. So I'm going to do this in general first. F of x is 18 over x. So f of x plus h is a lot easier to do than it has been on the last few problems. Literally, you just put x plus h where this x is. 18 over x plus h, that's literally f of x plus h. There's nothing to simplify. Minus the original f of x is just 18 over x, literally, all over h. But we can't plug 0 in because the denominator would be 0. But we can simplify the numerator with common denominators. Sometimes the only common denominator is taking each one and multiplying them together. Both of these denominators multiplied together is the common denominator. And then what happens is you take the first fraction and you multiply it by the second denominator to its top and bottom. And then the second fraction, you multiply the first denominator to the top and bottom. So we get 18x. Now, watch out for this. I like to do this and put plus a negative and take that negative with you when you multiply. Negative 18x, negative 18h, all over the common denominator. And this 18x cancels this negative 18x. So we're left with limit as h approaches 0 of negative 18h over this. And you could distribute it out, but I'm not going to. All over h, or think of it as h over 1. So that way you could have a fraction divided by a fraction. I teach this to a lot of classes from algebra all the way up to calculus. When dividing fractions, don't be shy. Flip the second and multiply. It's a nice way to get fractions inside of fractions away from that situation. So if I multiply top and bottom by 1 over h, the entire denominator cancels out and you don't have fractions inside of fractions anymore. And because there's no addition or subtraction up here, this h can cancel that h. That's the first time we no longer have an issue plugging 0 in anymore. The top, we have a single fraction, and the top is negative 18, and the bottom is x times x plus h. And even though there's an h still in the bottom, plugging 0 in does not make the bottom 0. The bottom becomes just x squared. So the derivative of 18 over x is negative 18 over x squared. X times x is x squared. So there's the original function. The derivative function is negative 18 over x squared. And that's the first answer. And then I think it's like number 6 where they want me to plug in numbers after that. Negative 18 over x squared is the generic version of the derivative. Now find f prime of negative 3. So plug it into the derivative function, not the original one. Negative 3 squared is positive 9. 18 divided by 9 is 2. And then this negative makes it negative 2. So if you knew what this graph looked like, and you went to -3, there would be a slope of -2 there. In fact, 18 over x is similar to 1 over x, it's just steeper. 18 over x basically looks like this. So if you go to -2 on the x-axis, or I'm sorry, -3, the slope there of the tangent line would be -2. So let's say it's -1, -2, -3 right there. This would have a tangent line slope of -2, which that looks about -2 right there. Down 2 over 1. Maybe not quite that, but that's a rough estimate of it. Okay, next is a check answer. Now plug 0 in, but -18 divided by 0 squared is undefined. So the derivative does not exist there, and that makes sense because the graph doesn't exist there. You can't do a tangent line at a spot where the original graph doesn't have anything. So the derivative doesn't exist at 0 because the graph doesn't exist, the original function doesn't exist at 0. That was a problem earlier in this section about that same idea. And then finally I can plug in 2. 2 squared is 4, so you get -18 over 4, which reduces to -9 over 2, so about -4.5. If you were at 2 on the x-axis, 1, 2, they're saying this slope is -4.5, although that doesn't look great, but I'm just estimating here anyway. So if I drew it better, it would be a slope of -4.5. Okay, so I wanted to do 6 first because polynomials are a little different than the way these rational functions have derivatives. Here's one that's quadratic. Equation of the secant line and equation of the tangent line. Okay, we can do that. Same thing. Find x values that does not have a derivative. Okay, that's good. This is another good one. Okay, so 7 and 8 are similar. Let's just do 7. Seven gives me f of x equals x squared plus x. Part A is about the equation, not just the slope, but the equation. Equation of the secant line. Whoops. Equation of secant lines, that's related to the average rate of change. So we want to go between -2 and +2. So f of 2 minus f of -2 over 2 minus -2. F of 2 would be 4 plus 2, that would be 6. That would be 4 plus -2, that would be 2. The bottom would switch to 2 plus 2. So 4 over 4 is 1. So if I drew some kind of quadratic and went between -2 and +2, the secant line slope would be +1 is what that's saying. And then if we want the equation of it, y equals mx plus b, well, we know m is 1. And then we can pick either 2 or -2. I'd probably pick 2. So when x is 2, f of 2 equals 6. So that's an x and a y coordinate. So you can temporarily plug in 6 for y and 2 for x just so you can find b. And that's 6 equals 2 plus b. This is done in algebra all the time. Subtract 2, b equals 4. So the equation of this secant line is y equals x plus 4. This line has a slope of 1, and if you backed all the way up to the y-axis, it would cross at 4 is what that's saying. So y equals x plus 4, that's the equation of the secant line. The key is to do the average rate of change to get the slope of the secant line. Secant lines are about average rate of change, and they're like the slope formula from algebra. The equation of the tangent line, you need the slope of the tangent line first. That's the concept of derivative. And we need to do it. The equation of the tangent line when x has the first value, so I guess they want that at -2. Okay. On the other one, it didn't matter which point we used because a secant line goes through both of those points, but a tangent line only goes through one point. So then we have to know which one they want us to do it at. So they said do it at the first one. Notice this part didn't say first or second because it actually goes through both of them, but this one says first. So they want us to do it at -2 in essence. So you could do the derivative in general first and then plug in -2, or if you just need -2, you could do it at -2. Either way, so limit as h approaches 0. I'll do it in general first just in case I need other points later. F of x plus h minus f of x all over h. For squares, it's not so bad. The original f of x is x squared plus x. So we need to do x plus h squared, that's taking the place of this x right there, plus another x plus h, taking the place of that x. But there's no numbers here to distribute. So that whole bracket is f of x plus h, minus, now put the original f of x in the second bracket, all over h. We've squared binomials out before, so you're going to get an x squared. X times h gets doubled to 2xh. And then you get h squared. And it turns out there's 5 terms here. None of them are like terms. So we just write all 5 of them down. X squared plus 2xh plus h squared plus x plus h. All 5 of those are different. There's 2 terms here, so I'm going to put the negative, and they'll both turn to negative, and they should both cancel out. Negative x squared cancels positive x squared. Negative x cancels positive x. 3 terms remain. None of them are like terms, and they all have an h, so you can factor out an h. 2x plus h, and that would be plus 1 literally. h's cancel. The only place to plug a 0 in is right there. So I would be left with the 2x plus 1. This is f prime of x. In general, f prime of x is 2x plus 1. So whether I want to do f prime of -2, or even I could even do f prime of 2, it's not going to help in this problem, but I could know it if I want to. 2 times -2 is -4, plus 1 is -3. So the slope of the tangent line at -2 is exactly -3. So the equation of the tangent line has to take the format -3x plus b. And we have to plug -2 in. We don't have a choice because tangent lines only happen at one spot, not 2 spots. And then we would need to know what is the y value when x is -2, which can only be found in the original function. So we need to do f of -2 to know that. -2 squared is 4, plus a -2 is 2. So I would temporarily put a y value of 2 in, and an x value of -2, and it's because they asked me to do the first point, not the second one. If I redid this with 2, I would get a totally different answer, because on a curve, you're constantly changing your slope. So that's why it matters which one they ask you to do. 2 equals, that's 6 minus 6, b equals -4. So the equation of the tangent line is y equals -3x minus 4. So a line that goes through -4 on the y-axis has a slope of -3. That would hit this curve like so, where it would just touch it once somewhere. I'm just making up that graph, but that's the concept that's happening, is you're touching that graph at one spot when x is -2. So -3x minus 4. When you do derivatives, they often ask you to find the equations instead of just the slopes. If they ask for the slope, that comes directly from the derivative. The equation, you got to go back to algebra and do y equals mx plus b. So this is the same kind of question, just the function is different. Find the x values where the graph does not have a derivative. So you can't do, there's actually some more spots. You cannot do a derivative any place the function itself doesn't exist. We already know that one. We also know another one, you can't do derivatives at vertical tangent lines. So if there was any spot along this curve that was vertical, there isn't, but if you get somewhere where there's a vertical portion, you can't do the derivative there. And another issue that causes us problems in calculus is corner points. You can't do the derivative at a corner point because it's like you can't put a tangent line on there. It's like everywhere at once, since it just like boom changes directions instantly. So that's no good to have a corner point. But it looks like that's the only issue here. Everything else is a smooth curve. Smooth curves you can find derivatives of everywhere, because there's always a tangent line slope in all these spots. So it looks like x equals 3 is the only issue on this one. We don't have any undefined spots like holes in a graph or asymptotes. We don't have vertical spots. So only that corner point is causing a problem. List the points on the graph where it's not differentiable. So we can't do it at this spot exactly here because the graph just kind of stops at that point. But notice they didn't put or equal to. So it's okay that I can't do it at -2. And then this is a smooth curve all the way till this corner point. So two's definitely out. Can't do the derivative at a corner point. And then this is a smooth curve, except there's a hole in the graph right there. So you're not going to be able to do that, even though it's defined somewhere else. This is going to fail that idea about continuity. The limit answer is going to be different than the function answer. And if it's not continuous at a spot, you can't do the derivative there. So 4 is another spot that's an issue. So you just put a comma and add that one. And then here's another break in the graph. So that's an issue 6. But everything else here is smooth, straight, so there's no issue in that portion of the graph. And we don't care about 7 exactly because they don't have the or equal to. So places where the graph stops could be an issue if they gave me a larger domain to go from. But we got those 3 issues right there. Okay, for the function of the graph, give the intervals where the rate of change is positive, negative, or 0. Okay, so positive. Okay, so start at this exact spot here, and you can't do it at a stopping point. So we don't need to worry about B exactly, but just past B. So notice that if you tried to put tangent lines on this portion of the curve, they're all aiming downward. These all have negative tangent slopes. So the derivative is negative this whole portion of the graph. And then right there when it changes directions from going down to going up, at that moment right there, then there would be a horizontal tangent line. So that's when it's 0. And now here's a portion where the graph is increasing. Increasing portions of the graph from algebra, that's when slopes of tangent lines will be positive. So all the way from 0 until that upper point, I guess this is 10, 20. From 0 to 20, you're going to have positive tangent line slopes. And then it's negative ever after that. So do they have 0 to 20 only? Yeah, 0 to 20 only is the only portion where it's positive. Derivative will be positive at that portion. It's negative from this arbitrary starting point of B all the way till 0, and then again from 20 all the way to this arbitrary point of C. So from B to 0 and from 20 to C, that's where the rate of change would be negative, because that's where the tangent lines would have negative slopes. And there's 2 times it would be 0, exactly at 0, and then right there exactly at 20. So when it changes from decreasing to increasing, or changes from increasing to decreasing, those exact spots, that's when the tangent line slopes would be 0. So both 0 and 20, that happens. Identify graph 1 or 2 represents velocity. Which one represents distance? Okay. It says consider when the derivative is 0, positive, or negative. Okay, so look at these flat spots right there. I could draw a horizontal tangent line right there at x equals 2. So if this is the original graph, then that means the derivative graph has to have a spot on its graph where you're at 0 when x is 2, which is literally right there. See how the graph crosses through the x-axis at 2? The y value at 2 of graph 2 is 0, and that's because the slope of the tangent line in graph 1 is 0 at that spot. And same thing at this spot, and same thing down here. It's hard to tell what that is, but when x is 4, there's another spot where the tangent line would be 0 here. So on the derivative graph, you should be crossing the x-axis at that point, and it is. Where the opposite is not true. If I thought this was the original graph, then at both 1 and 3, I should be crossing, well, actually it is. So I guess it could be either way. So then we need to look at some other things like where is the slope positive and negative. So notice that the graph decreases here, but then it increases. So any portion where a graph is decreasing on the original graph, on the derivative graph, you would be below the x-axis. And then when it increases, then you're above the x-axis. It's decreasing all the way to 4, you're below the x-axis, and then it's increasing from 4 and beyond, then you're above the x-axis. So does that happen here too? No, because see, at the beginning of this, from that whole portion, you're increasing on this graph. So that should be all above the x-axis here, and it's not. So this graph 2 cannot be the original function, because then this derivative function wouldn't work. So graph 1 needs to be the original, and graph 2 needs to be the derivative graph. And in physics, original is distance or position, derivative is velocity. So since graph 2 has to be the derivative, then graph 2 has to be the velocity. So that's this one, the second option. And then, okay, this is when h is small. Okay, so this will take a while to read through all these, but do your best on that one. Is this the last problem? Oh, no, this goes for a while, huh? So again, we're about an hour and a half in, and now we're getting some of these business application problems. So again, see what you can do with these, and if you have any issues with them, email me. If you email me, I can take the time to explain it to you, where I don't want this video to just drag on just because one of these problems might take 15 or 20 minutes to do. Okay, so that's a good stopping point. We've covered at least the most important topics in section 3.3 and 3.4. You have a good idea on how to do average rate of change, instantaneous rate of change, and then derivative calculations with numbers and with variables. So the video is exactly an hour and a half, and I'll sign out for Tuesday, July 26th, and see you tomorrow, Wednesday, when we do 4.1 and 4.2.